Good morning, everybody, and welcome back to Next Door NetAdmin. I have mentioned ZFS a couple of times, I want to say, on this channel, but always in passing. I mentioned it when I was setting up a new OpenSense server, and I went into a little bit of detail, but I thought that today I would go into more detail and let you know more of how it works, why I'm interested in it, and why I think it's beneficial. Sound good? Cool. So ZFS is most likely, in my mind at least, to be compared to a traditional RAID system. In a traditional RAID system, you have multiple disks that are all working together, and you will have different topologies, different setups for how you want those disks to work together. For example, in a RAID 0, it's just a stripe. It's a stripe across multiple disks. If you lose any of those disks, everything's gone. All you benefit from is the increase in speed by having each write spread across multiple disks. You have RAID 1, which is a mirror. Every write is duplicated onto 2 disks. You don't get any increase in speed, at least not on the write. You can get an increase on speed if your controller handles it properly. But you do get redundancy. You do also, however, have 2 duplicate copies, so you only get to make use of half of your total disk space. There's other topologies. RAID 3 used to be common, not anymore. RAID 4 used to be out there, not anymore. RAID 5 used to be pretty common. It is a stripe across multiple disks, but with parity. And this means that you can lose one disk, up to one disk, not more, and the additional parity that's been calculated and written to disk will fill in the blank and allow the machine to calculate the missing data. Cool. If you lose more than one disk, everything's gone. RAID 6, similar, except parity is calculated in 2 dimensions. Dimensions, what is this? Don't worry about it. It's a computing term. You don't need to get into the details of that. You can think of it as 2 different calculations of parity, such that in RAID 6, you can lose up to 2 disks, and you can use the different parity calculations to reconstitute the missing data from up to 2 disks. But again, not more. If you lose more than 2 disks, everything's gone. RAID works on whole disks. That's it. It just either knows the disk is there or the disk is not there. It does not have a way to say, is the data being returned by this individual disk good or bad? RAID is also file system agnostic. It doesn't care whether you're running NTFS or FAT32 or ext4 or anything else. It doesn't care. To a RAID controller, all of these disks are simply block devices, and it presents in return a single logical block device. It says, here is a disk drive, do with it as you wish, and the RAID controller handles the details of managing the disks. This is a very layered approach. It's not a network layer. We're not going to go into the OSI networking model at this point, but it is a very layered approach. You have disks, you have RAID, then you have the file system, then you keep going. When you have data split across multiple disks, either with RAID 0, RAID 5, RAID 6, whatever, one of the settings you need to choose is a stripe width. And what's the word I'm looking for? I'm having a moment of just brain blankness. This is great. This controls the amount of data that is sent to each disk. So if you have a 128 kilobyte stripe width, it doesn't matter if you only have a 4 kilobyte file to write. You got a 4 kilobyte file? That's nice. It's a 128 kilobyte stripe width. So you have to read in 128 kilobytes of data from all your disks. You have to recalculate your parity with the changes from the 4 kilobyte file, and then you have to write 128 kilobytes back. This is also known as RAID write amplification, because you gotta write in your stripe width. And you can choose a smaller stripe width, say 32 kilobyte, 64 kilobyte, and that's better if you're working with lots of small files. Or you can go bigger, like 256, 512. I've even seen some these days that have a full megabyte stripe width. That's better for large files because it's fewer separate reads and writes that needs to be done. But if you have small files, your write amplification is going to be hitting you pretty hard. The crucial point is this is a decision that can only be made once when you're setting up the array. You can't change it afterwards. You'd have to delete the array and reset it, because once it's set, all of your data is written in this stripe width, period. That's just how it is. So, ZFS. Let's talk about that. ZFS has a lot of powerful features, but it breaks the layered assumption of disks, RAID, file system. And it does this because the file system has information that can optimize the way the RAID is handled, and the RAID can do a better job if it has more information about the actual disks that it's controlling. So, before I get too far into the details, there's one other thing that I'm going to mention. It's pretty common among server admins and network admins to say, hey, if you're going to be working with RAID, you want a hardware RAID controller. You don't want software RAID. Why is this? Software RAID relies on a specific driver. If you don't have the driver, you can't talk to the RAID. A hardware RAID will typically, like I said, present just an abstract, here is a block device, it is a disk drive, do with it as you wish, and then the RAID controller will handle the details. Hardware RAID also has its own onboard chip, essentially. And that can handle splitting the data, it can handle reading the data, it can handle doing the parity calculations, depending on how good that chip is. And it doesn't have to be micromanaged, essentially, by the operating system. Cool. So ZFS, being a file system, it's not a hardware controller, it's software. Does that make it worse? There are ways that you can mitigate this, and ZFS uses them in order to prevent itself from becoming an undue burden on the system and slowing down performance. Okay, so let's start by talking about the actual physical setup of ZFS. In ZFS, your main central storage array, as you might call it, instead of a RAID array, it's called a Z pool. It is a pool of storage, and from there, you can carve out sections of it to do various things, and we'll get to those in a little bit. But your Z pool is composed of one or more vdevs, virtual devices. Each one of these vdevs can be a different topology. It's up to you. You can have a single disk as a vdev, if you want. You can have a mirror of disks as a vdev. You can have 3 disks as a mirror. It's a 3-way mirror. You can have n-way mirrors. How many copies of data do you want? You want 5 disks, all with the same data? You can do a 5-way mirror. Up to you, your choice. You can do a RAID Z1, which is similar to RAID 5, but it's not actually RAID 5. We'll cover the difference in a moment. But RAID Z1, similarly, has the ability to take one drive failure, and the vdev will keep running. The vdev will not have failed. A RAID Z2, again, you can lose up to 2 disks and the vdev will continue functioning. RAID Z3 does its parity calculations in 3 different dimensions, so it can take up to 3 drive failures and keep running. This is all very well and good, but like I said, each vdev can be a different architecture if you want in the Z pool. Excuse me. So that means you could have a mirror, you could have a RAID Z1, and you could have a RAID Z3, all part of the same pool, but with different topologies. Where is this useful? I don't think it is, but it's a thing that can happen, and this is why you need to be aware of it. All data in the Z pool is striped across all the vdevs. This is how it works. So if you add a new vdev, as new data is coming into the pool, it will be striped across all of those vdevs. And if you happen to have a vdev that is a RAID Z1, for example, then the data for that stripe will then be striped across the various disks in that array. Excuse me, in that array, in that vdev. Terminology. However, if you make the mistake of accidentally adding a single disk vdev to your pool, what have you just done? Well, you can't remove a vdev from the pool once you've added it. That is one of those things that you don't get a redo on that. If you've added a single disk to your pool, you've essentially slowed down the performance of the pool to that of a single disk, because a single disk has to be part of all the data read-writes. And if that one disk fails, boom, now you've lost your pool. That's it. There is no redundancy at the pool level. The redundancy is provided by the vdevs. If you have a pool which is one mirror, okay, you can lose a disk out of that, the pool survives. If you have 2 mirrors, you can lose a disk here, you can lose a disk here. Your vdevs are still functional, and so your pool continues. If you have 2 mirrors and both of these disks die, now your pool's broken. You've lost one of your virtual devices. And so when you have it striped across the 2, to have lost one of this vdev is the same as having 2 single devices in RAID 0 and losing one of those. Your data is lost. So if you have multiple vdevs, but one of them is a single disk, if it goes, everything goes. And it's remarkably easy in some cases for new admins or admins who are distracted, not paying attention, whatever, to accidentally add a single disk vdev. And now you're kind of stuck with that. There is, I think, one way that you can fix this somewhat is by upgrading it, by converting a single disk to a mirror. I think that is something that you can do. And you can also break a mirror by setting one of its devices to be offline. But that's not something that you want to do. And it's really kind of not optimal. If you want a topology where you have one vdev as a RAID Z2 and another vdev as a RAID Z2, and now you've got a vdev which is just 2 disks in a mirror, that's not going to have the same read or write performance as these other vdevs where you've got, I don't know, say 4 disks in RAID Z2 and 4 disks in RAID Z2. When you're reading and writing, you can pull from 4 disks at once. Whereas this one, where you're stuck with 2 disks for the same amount of data, because again, it's striped, which means that if the capacity of the vdevs is the same, then the same amount of data is going to go to each. ZFS is also intelligent about this. If you have let's say 3 vdevs, just because that's the example we're going with. If you have a vdev that was 50% full, and you added a new vdev, which is obviously 0% full because it's brand new, ZFS will put the data proportionally more on the new vdev because it has more free space available. So it'll try and balance the workload according to how much storage is available, but not necessarily according to performance. It's by capacity. So it's best if you, the administrator, figure out how you want this topology to work and be really confident about it. Be really careful when you're adding new devices because there is no undo button for adding a new vdev. Do it wrong and you might have broken your entire setup. That's fun, isn't it? For certain values of the word fun. So that's the vdev level. And it's important to note that you can kind of replicate a traditional RAID setup like this. If you have multiple mirrored pairs and then you're striping across them, a stripe over mirrors, that's a RAID 10 in typical speech. If you have multiple RAID Z1s, okay, you're now running a RAID 50 or RAID 60 if you're using RAID Z2s. There is no RAID equivalent for a RAID Z3, so it just is what it is. Not a lot of people I know of actually run RAID Z3 either. It's an option, same as using a single disk is an option. That doesn't mean that a lot of people want to use it. What separates RAID Z1, RAID Z2 from correspondingly RAID 5 or RAID 6 is another feature that ZFS has, which is why fix yourself to an arbitrary 128 kilobyte stripe size. Because ZFS is also the file system, it knows how big the file is. I'm only writing a 4 kilobyte file. Let's use a smaller stripe size for that. I'm writing a 5 gigabyte file. Small stripe size isn't the best way to go. Let's use a bigger stripe size. ZFS uses dynamic stripe width according to how much data it has to write in each transaction group. It's not per file necessarily, but depending on how many writes are being accumulated at any given point in time, it will set a dynamic stripe width based on that. So it's trying to make sure it doesn't have to do more calculations and more reading or writing than it actually has to do. This is intelligent. ZFS, because it has direct control of the disks, and this is why it's very important that you never, never, never run ZFS on a RAID controller, because the RAID controller abstracts all the disks away and just says, I have one big logical drive, use it. So you can't actually look at all the disks. ZFS, you want to have each individual disk individually addressable with no RAID whatsoever. And when you do this, suddenly ZFS can say, okay, so I pulled data from 2 different drives in a mirrored pair. I got XYZ out of one, and I got XAZ out of the other. Because ZFS saves a checksum of every block of data, it can look at the data that's returned and says, actually, according to this checksum, XYZ is correct. XAZ is incorrect. So transparently, while I'm reading that data back, let's say this disk has an incorrect copy of the data, let's fix it. Just silently, let's go fix that. It'll check it on a file-by-file basis. This is very different from traditional RAID. With traditional RAID, you don't have a file-by-file confirmation that the data is correct. It's either the disk is there or the disk is not there. If you have a failing disk in your RAID, that can end up passing you corrupt data. And in particularly bad cases, you can end up with the RAID controller saying, hey, I've got mismatched data and I don't know which is correct, so puncture! If you get a RAID puncture, there's not a lot you can do. You have to erase the entire array and start over from scratch, which is a real drag. So ZFS can avoid this by actually checksumming the data and seeing which drive is good, which drive is bad, and fixing it on the spot, or marking it as, hey, this sector is an issue, let's remap it or do whatever else we have to with it. You can also do a preventative scrub of your data. Not necessarily during production hours, because a scrub is kind of intensive, but during a scrub, it will read all the data back on each drive, verify everything is correct, and proactively check for any errors. And then if it finds some, it'll rewrite the data because it has a checksum. It can tell you what the correct data is. So ZFS has a lot of features like this where, because you have dynamic stripe width, you're reducing the performance requirement of having to pull back lots of data, read it, update it, write it back. You're getting rid of your write amplification. You've got checksumming of individual blocks of data, individual files. It's actually blocks of data, but hey. You've got a choice of topologies that will do pretty much whatever you want it to, but you have to be careful to set that yourself and make sure that you put some forethought into it. Then there's other things that you can do. ZFS by default uses system RAM as a cache for data. It's an adaptive cache, which means that it will cache the data that is most frequently used, even if it's not the most recently used. You can add a second level of cache, level 2 adaptive read cache, Your L2 ARC can be another SSD, fast device, cool. You've got layer 2 cache. You can do an SSD for a separate log device or a slog. This holds the ZFS intent log, which is similar to a battery-backed cache on a RAID controller, where typically this would accumulate writes. It's got a battery so that if you have a power outage, before it can write that data out to disk, it'll keep the cache, it will have a battery to keep it powered, and then when the power comes back on, the first thing it does is write out anything that was still pending back to the disks. ZFS does much the same thing, except instead of having a battery-backed cache, it has the ZFS intent log, what it intends to write to the disk. And so it will take any writes that are inbound, save it to the ZIL, the ZIL, and then when it has gathered enough data to make a transaction group about every 5 seconds, or when there's enough data to actually make the write worthwhile, then it'll write it out to the disks. So there are other devices that you can add there too. There are other new devices. There's metadata only devices. There's special devices, which I haven't used honestly yet, so I can't tell you a whole lot about them. But this kind of setup can be frustrating for traditionalists who go, it's breaking the layer architecture. I mean, disks should be separate from RAID, should be separate from file systems, so that everything is self-contained. I get that, I do. But in this case, there's also a lot of benefits that come from your file system being able to say, hey, these are separate files. They shouldn't necessarily have to go into a 128 kilobyte strip. That doesn't make sense. These are huge files. Putting them in a 128 kilobyte strip, again, doesn't make sense because they're huge. Use a bigger stripe. Your file system can tell you that. Your disks can tell your RAID, hey, yeah, I'm the one returning bad data, fix me. And the system can go, okay, Here's a fresh copy of the data. Save that. Thank you very much. There's a lot of useful and powerful features that can come with ZFS. I have run out of time for today. I was going to tell you about data sets and zvols and all the other fun stuff that you can do with that. But for now, we're going to leave it at that. Just a discussion of the physical setup and some of the features that it has to increase performance. So, like I said, that's it for now. Thank you very much for watching. I am your next door NetAdmin, and we'll see you next time.